In September of 2015, an instrument spread across 2 sites in the United States, one in Louisiana, one in Washington State, measured a distortion in the fabric of space itself, smaller than 1/10,000th the width of a single proton. That measurement confirmed something Albert Einstein had predicted almost exactly 100 years earlier. It also confirmed something else. For most of those 100 years, even Einstein himself didn't think anyone would ever actually be able to detect it. This is the story of how that changed. It's a story with real decades of failure in it. A scientist whose reputation was permanently damaged by a false claim, and an instrument so absurdly sensitive that building it required inventing entirely new categories of precision engineering along the way. Let's start at the beginning, in 1916, the year after Einstein published his general theory of relativity. General relativity described gravity not as a force pulling objects together, the way Isaac Newton had described it, but as the curvature of space and time itself, warped by the presence of mass. A natural consequence fell directly out of Einstein's own equations. If massive objects accelerate in the right way, they should send ripples through that curved fabric of space-time, propagating outward at the speed of light, exactly the way a stone dropped in a pond sends ripples across the water's surface. Einstein called them gravitational waves, and he wrote the paper predicting them in 1916. Here's the part that tends to surprise people. Einstein himself spent much of the following 2 decades unsure whether gravitational waves were even a real physical phenomenon, or just a mathematical artifact, an illusion produced by the particular way he'd set up his equations, rather than something genuinely rippling through the universe. In 1936, working with a younger physicist named Nathan Rosen, Einstein actually submitted a paper to a physics journal arguing that gravitational waves didn't exist at all, reversing his own earlier prediction. A peer reviewer at the journal caught what appeared to be an error in that paper, and after a fairly public dispute over the review process, Einstein and Rosen revised their conclusion, ultimately deciding gravitational waves probably were real after all. Even the person who invented the theory wasn't fully sure, for years, whether his own prediction actually held up, and even once physicists broadly agreed gravitational waves were theoretically real, an even bigger problem remained. Could they ever actually be measured? The effect is almost unimaginably small. Only the most violent events in the universe, colliding black holes, colliding neutron stars, produce waves strong enough to even consider detecting from Earth. And by the time those ripples cross the vast distances between galaxies and reach us, they've weakened to almost nothing. Detecting them would mean measuring a change in distance far smaller than the width of a single atom. For decades, most physicists considered that a purely theoretical curiosity, fascinating on paper, essentially impossible to ever actually build an instrument for. The theoretical debate over whether gravitational waves carried real physical energy, rather than being some kind of mathematical illusion, wasn't fully settled until 1957 at a conference in North Carolina. A physicist named Richard Feynman, already well known for his sharp, often blunt way of cutting through confusion, offered what's now remembered as the sticky bead argument. Picture a rigid rod with a bead loosely threaded onto it, free to slide with a bit of friction. If a gravitational wave passes through, Feynman argued, it would stretch and compress space itself, causing the bead to slide slightly back and forth along the rod, generating friction, and therefore heat. Heat means energy. And if gravitational waves could generate real, measurable heat, they had to be carrying real physical energy, not just describing an abstract mathematical wobble in Einstein's equations. That simple thought experiment effectively ended the theoretical argument. Gravitational waves were real. The only question left was whether anyone could actually catch one. The first person to seriously try was a physicist named Joseph Weber at the University of Maryland, starting in the 1960s. Weber built large aluminum cylinders, several feet long, designed to physically vibrate ever so slightly if a gravitational wave passed through them, the way a bell rings when struck. By the early 1970s, Weber announced he detected signals, coincident vibrations showing up simultaneously in detectors he'd placed in different cities. It was front-page news. For a brief moment, it looked like the impossible had been achieved. It hadn't. Other research groups built similar bar detectors, attempting to replicate Weber's results, and none of them found anything. Careful statistical analysis of Weber's own data suggested his detection claims didn't hold up. The scientific consensus gradually, and fairly publicly, turned against him, and Weber's reputation never fully recovered, even though he kept defending his results until his death in 2000. It's a genuinely uncomfortable chapter in the history of this field, a reminder of how easy it is to convince yourself you found a signal buried in noisy, technically demanding data, especially when you're the one who spent years building the equipment hoping to find it. The first real, credible evidence that gravitational waves existed came not from a direct detection at all, but from something more indirect and considerably more elegant. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar, a pair of incredibly dense, rapidly spinning neutron stars orbiting each other, one of which beamed out radio pulses with the reliability of an extraordinarily precise clock. Using those pulses to track the pair's orbit with remarkable precision, Hulse and Taylor found that the two stars were gradually spiraling closer together over time, losing orbital energy at almost exactly the rate general relativity predicted they should, if that lost energy was being carried away by gravitational waves radiating outward into space. It wasn't a direct detection. Nobody measured a passing wave here on Earth, but it was powerful, indirect proof that gravitational waves existed and behaved exactly the way Einstein's equation said they should. Hulse and Taylor won the Nobel Prize in Physics for the discovery in 1993. That still left the original problem unsolved, actually catching one directly, here on Earth. The solution that eventually worked was an instrument called an interferometer. And the concept behind it is almost deceptively simple, even though building one turned out to be one of the most demanding engineering projects in the history of experimental physics. Here's the basic idea. Split a single laser beam in two, sending each half down a separate, perfectly perpendicular tunnel, several kilometers long. At the far end of each tunnel, a mirror reflects the beam straight back toward where it started. Under normal conditions, both beams travel the exact same distance and recombine perfectly back where they began, canceling each other out in a very specific, predictable way. But if a gravitational wave passes through, it stretches space very slightly in one direction, while compressing it in the other, meaning one beam now travels an infinitesimally different distance than the other. That mismatch shows up as an extremely faint shift in how the recombined light behaves, a signal you can, in principle, measure. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, was built on exactly this principle, with two L-shaped detectors, each with arms 4 kilometers long, constructed thousands of miles apart, in Louisiana and Washington State. The distances involved in that measurement are almost impossible to picture intuitively. LIGO needed to detect a change in the 4-kilometer arm length smaller than 1/10,000th, the width of a proton, one of the smallest particles that makes up an atom's nucleus. To achieve that level of precision, engineers had to solve problems that had never seriously needed solving before, isolating the mirrors from virtually every source of vibration on Earth, including distant traffic, ocean waves crashing on shorelines hundreds of miles away, and even the subtle seismic hum of the planet itself. Built in some of the purest vacuum chambers ever constructed, so stray air molecules wouldn't scatter the laser light, and developing mirror coating smooth and stable enough that quantum-level fluctuations in the mirror's own atoms became one of the primary sources of noise the team had to account for. An initial version of LIGO ran from 2002 to 2010 and detected nothing, which wasn't a failure exactly, since the instrument's sensitivity at the time was known to be right at the edge of what might be needed. It was more of a necessary proof that the basic approach worked well enough to justify a major upgrade. That upgrade, called Advanced LIGO, came online in 2015 with dramatically improved sensitivity. On September 14, 2015, just days after Advanced LIGO officially began its first observing run, both detectors in Louisiana and Washington registered an almost identical signal within milliseconds of each other. A brief rising chirp, a signal that swept upward rapidly in frequency before abruptly cutting off. After months of careful verification, ruling out instrumental glitches, environmental interference, and every conceivable false alarm the team could think to check, the LIGO collaboration announced the discovery in February of 2016. The signal, designated GW150914, was the unmistakable signature of two black holes, one about 36 times the mass of our Sun, the other about 29 times, spiraling into each other and merging into a single black hole, roughly 1.3 billion light-years away. In a fraction of a second, that collision released more energy in the form of gravitational waves than the combined light output of every star in the observable universe, briefly outshining the entire visible cosmos in a form of radiation no telescope had ever been able to see. Three scientists central to LIGO's development, Rainer Weiss, Barry Barish, and Kip Thorne, were awarded the Nobel Prize in Physics in 2017 for the achievement. The story doesn't end there. And in some ways, the most scientifically important detection came almost exactly 2 years later. On August 17, 2017, LIGO and its European counterpart Virgo detected a different kind of gravitational wave signal, one consistent not with colliding black holes, but with two neutron stars spiraling together and merging. This time, unlike every previous detection, telescopes around the world were also watching. Within seconds, a gamma-ray burst was detected coming from the same region of sky. Over the following days and weeks, dozens of observatories turned toward the source and captured it across essentially the entire electromagnetic spectrum: visible light, infrared, ultraviolet, X-rays, and radio waves, all from the same collision. That event, cataloged as GW170817, marked the beginning of what astronomers now call multi-messenger astronomy, studying a single cosmic event through completely different physical channels at once, gravitational waves and traditional light, arriving together and telling a more complete story than either one could alone. Among the discoveries that came out of analyzing that light, strong evidence that collisions between neutron stars are a major source of the universe's heaviest elements, including gold and platinum, forged in the extreme, neutron-rich environment of the merger itself, and flung out into space. In a very direct sense, some of the gold on Earth likely traces its origin back to an event exactly like this one, sometime in the galaxy's deep past. In the years since those two landmark detections, LIGO, Virgo, and a third detector in Japan, called Kagra, have detected gravitational waves from well over 100 additional merger events. mostly colliding black holes, along with a handful of additional neutron star mergers. That growing catalog has already started reshaping astrophysics in its own right. It's revealed black holes with masses that sit awkwardly inside a theoretical mass gap, a range that standard models of how massive stars die and collapse struggled to explain, forcing physicists to reconsider how some black holes actually form. It's also let researchers measure the universe's expansion rate through an entirely independent method from traditional approaches, offering a fresh way to investigate a stubborn, ongoing discrepancy in cosmology known as the Hubble tension. None of this is finished. Ground-based detectors like LIGO can only pick up relatively high-frequency gravitational waves, generally limited to the final violent moments before two compact stellar mass objects merge. An entirely different category of gravitational wave sources, much larger, much slower events, like the gradual, long-term inspiral of two supermassive black holes at the centers of merging galaxies, produces waves at frequencies far too low for LIGO to ever detect from the ground, since Earth's own unavoidable background vibrations drown out anything that slow. The proposed solution is to leave Earth entirely. The Laser Interferometer Space Antenna, known as LISA, a joint mission led by the European Space Agency with NASA participation, is planned to place 3 spacecraft in a triangular formation, trailing behind Earth in its orbit around the Sun, each separated from the others by millions of kilometers, using laser links between them to detect the much slower, lower-frequency ripples that ground-based detectors simply can't reach. LISA is currently targeting a launch sometime in the mid-2030s. Meanwhile, next-generation ground-based detectors, including a proposed underground facility in Europe called the Einstein telescope and a planned U.S. counterpart called Cosmic Explorer, aim to push sensitivity roughly 10 times beyond what current instruments can achieve. It's worth sitting for a moment with just how strange the full arc of this story actually is. Einstein predicted gravitational waves in 1916, then spent years unsure whether his own prediction was even physically real. For decades afterward, most physicists treated direct detection as effectively impossible, a fascinating idea confined permanently to theory. A false claim in the 1970s damaged one scientist's career and briefly cast doubt over the entire pursuit. And then, a century after the original prediction, an instrument sensitive enough to measure a distortion smaller than a single proton finally caught the real thing. Not once, but now, well over 100 times, and opened up an entirely new way of observing the universe in the process. The universe had been sending out these signals the entire time, quietly rippling past Earth with essentially every violent collision that ever occurred anywhere in the cosmos. We simply didn't have ears sensitive enough to hear any of it, until remarkably recently. Beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.